Hello, good evening, good day, everybody, and welcome to the latest episode of the Ask Abhijit show. As you know, today we discuss science. I'm taking your questions about science. So, before we begin, let me take a look at who all is there. I can see GK, Tejas, Jai, Ananya, Pranay, Komal, Dharman, Karan, Nalavat, Vaibhav Gupta, Asminor, Aditi, Srinivas, Great Sir is back, Alpha, Vishal Kumar, Akshit, Himanshu, Intellectual Indian, Dungar Singh Chauhan, Samarth, a Korean name, Piku, India Unleashed as Minor, Trupti, Priyanshi, Zaina, Akshit, Sioram, Kush, and lots of other people. Great to be with you all once again this fine Saturday evening over here. So, shall we get into the questions? Let's begin with the questions. And what is the first question? The first question is by our friend Dungar Singh Chauhan. And the question is: the James Webb telescope was hit by a number of meteorites in May, which has led to some permanent damage. Will it lead to some significant deterioration in its performance? Okay, so yes, I'm not sure when this happened, but yes, this telescope was hit by one micrometeorite. What's a micrometeorite? A micrometeorite is a meteorite, a piece of space rock which is less than a gram in mass, in weight. Small, very small. Okay, so let's take a look at what sort of damage this telescope has suffered. Let me share my screen and let us do a search for the JWST mirror. There we are. There we are. 1 second. Give me a second. So, this is what the James Webb Space Telescope's mirror looks like. It's a hexagonal arrangement, as you can see. Yeah, it's a massive mirror, and it's made up of these segments. So A1, B1, A4, etc. I think the segment that was struck by the micrometeorite was a C3 segment. The C3 segment was hit and it's suffered a small amount of damage. So the thing about the James Webb telescope is that all of these different segments can be aligned individually. They all have their own little motors that align them. And over the past few months, each of these mirror segments was aligned in order to be able to give a proper image. So the JWST is designed such that in case one or two or several of these segments are damaged, they can be realigned using the motors in order to offset the effect of the damage, and it will still be able to produce a reasonably good image. So right now, I believe that the deterioration in the image quality is insignificant, despite this damage having occurred. So the thing is this: the damage which has happened is permanent damage. It's not going to be repaired because it's so far away. The telescope is so far away that nobody can go and repair it, and that's why this mechanism is inbuilt into this telescope. That if one of these segments is damaged, it can be realigned, and the overall image that is produced is still going to be good. So I think it's not uh, a significant setback. The images that this telescope is producing are still very much in. They are still exceeding the desired outcome, the expectations. So overall, it's fine. So it's not a number of meteorites. It is a single space rock, and that too a micrometeorite, less than 1 gram in mass. So it is not going to lead to significant deterioration in the performance. So the overall envisaged lifetime, the hoped for lifetime, the minimum lifetime for this telescope is 5 years, but it is expected, it is hoped that it will last for 20 years, hopefully. And yeah, they have obviously calculated the possible effect of micrometeorite damage and all that into all these calculations. So so far so good. It's still working fine. It's still going to give us great results, and we hope that there is no more, at least for some time, no more damage of this kind. Yeah. Okay, Master Sensei Gaming says, as the US is claiming to have found aliens, with its James Webb Telescope. What is your thought on it? As already the Japanese have claimed that they have seen them many years ago. Also, many Japanese have spent their life to find aliens and document what they found. Well, if people have been documenting aliens, where are the aliens? Show me. Where are the aliens? What's the documentation? Where is the documentation? Where's the proof? Now, this other claim that I'm hearing, like what we are seeing here, that the US is claiming to have found aliens. When did the claim happen? I have not seen any such claim. I have seen many YouTubers, including several Indian YouTubers, claiming that the James Webb Space Telescope has found life or aliens. First evidence of alien life or something like that. Where? I fail to understand how people can make such idiotic, ridiculous, baseless claims. I've seen multiple YouTubers making this claim that the James Webb Space Telescope has found life, alien life. What nonsense! It's found no such thing. Nobody has made these claims apart from people who are completely unconnected with this telescope. So here's how this telescope could possibly find traces, signatures, or signs of what could possibly be life. Okay, this telescope has got an infrared spectrometer, spectrograph, whatever you want to call it. So, what this instrument does is it takes images of spectra. So, let's say you are and this spectrometer, spectrograph, can take spectra from lots of different sources at the same time. Now, what is a spectrum? A light spectrum. It's like a light library, color library, light library. So when you are taking the spectrum from, let us say, an exoplanet, which is a planet in orbit around a distant star. So when you're taking the spectrum, the light signature, the light library from that exoplanet, you are essentially uh, cataloging the chemical signature, the chemical cocktail of that exoplanet. So when light, let's say you are looking at a forest, yeah, on Earth, you're looking at a forest or not. What you see the color green. That's what you see. Now, why do you see the color green? It's because the chlorophyll that is in the leaves of these plants and trees, it absorbs light in the red spectrum and blue spectrum. It absorbs red light and blue light, and it reflects back green light. That's why forests and plants look green. Now, if you were an alien with their own James Webb telescope, you are pointing it at Earth and collecting the light spectrum, you would see lots of blue and green. And you would see the distinctive signatures of something like chlorophyll and whatever composition of gases we have in our atmosphere, right? So that's a light spectrum. And based on the spectrum, these aliens could come to the conclusion that there is a very high likelihood of there being life on this planet, because we find the signature of chlorophyll and various other uh, gases in the atmosphere which are characteristic of a certain kind of life, right? So similarly, the James Webb telescope could look at other planets, exoplanets, and if it finds certain such signatures that are the characteristic signatures of Earth-like life, then one could say with a reasonable amount of confidence that there could be possibly life there. So then we could create a catalog of such interesting planets where there is a high likelihood of life, and then study them further through a variety of means. So that is what the James Webb Space Telescope can do. It's not going to detect aliens and say, hey, there's a photograph of 15 aliens having a party. It doesn't work like that. And thus far, from the results that have been released, it has uh, we have seen the result from a single exoplanet thus far, and that's a type of exoplanet called a hot Jupiter. It's called Wolf something. This particular exoplanet, it's a hot Jupiter, which means it's a Jupiter-like gas giant, which is very in a very tight orbit around its star. Which means it's the orbit is very small. It's The distance between this exoplanet and its star is less than the distance of Mercury from our star, from the sun. So it's got a very short orbit, orbital period, 3-4 days at most, and it's a very hot planet. And the telescope has f- examined the spectrum of this planet, and it's shown that there is water vapor in this planet's atmosphere, and there are clouds. But obviously, it's too hot to sustain any kind of life. So this is what we have found thus far: a giant gas giant, hot Jupiter kind of exoplanet, which contains water in its atmosphere, and obviously there will be clouds. So that's what we know thus far. That is not proof of life. That is not proof of life by any means whatsoever. So please understand that there is no claim that has been made of having found aliens or having found life or any such thing, right? So please keep things balanced. Don't get carried away by sensational reporting. Yeah, we are still a long way away from finding any aliens. But yes, so that's the potential that this telescope has. It will be able to identify interesting exoplanets where we should look further, because there could be life there. Yeah. So that's what this telescope can do. Thus far, we are in the beginning of the career of this telescope. So let me set the record straight. We have not found aliens thus far, at least. Now I don't know what the Japanese have been claiming. There is this entire industry that is built around you know the alien visitation industry. There are lots of people in various countries who are alien hunters or whatever, and they claim they have met aliens, or they've been abducted by aliens, or they have found aliens and whatnot. Where is the evidence? There's none. So, and since we are talking about aliens, let's take one more question about aliens. This is from quite some time ago, a month ago, but let's take a look anyway. So this is by Rani. The question is: the news broke out last year about an ex-Israeli space chief admitting the existence of aliens. It was said that both the US and Israel have some kind of contact with aliens, and allegedly Donald Trump also knows about this and was prohibited to expose the news to the public because people aren't ready yet. What's your take on this whole situation? Do you think the two countries are working together with aliens, or are these made up stories for maybe some other purpose? My question is very simple. Why would aliens only contact the US? Every time the claims of alien whatever contact happen, it's the US. When you see UFOs, it's always in American skies. Very soon we will see UFOs with McDonald's advertising, Pizza Hut advertising on them, because because these are American companies. The question is, why do UFOs only appear in American skies? Why do aliens only visit the US and maybe Israel now? Why? Aliens don't care about human politics, do they? They would not know anything about it. And if they do visit the earth, they should be visible in all countries, in all major countries. I've yet to see any Indians claiming to have seen UFOs or having been abducted by aliens. I've not seen any claims from India or China, for that matter. So why only the US? And now Israel is getting involved in this. So yes, I did see the news. I did read about this, that one of the ex-Israeli, I don't know, some kind of prominent person in Israel who is now retired, claimed that they have some kind of contact with aliens. So once again, that is a claim. Please understand the difference between a claim and proof. If I say I have shaken hands with aliens, it is a claim. It's a claim. I am making a claim, verbal claim. I am not showing you a photograph or a video of me shaking hands with aliens. So if this gentleman is claiming that he or his agency or his country is in contact with aliens, why doesn't he furnish evidence, convincing evidence, right? In undisputable evidence, photographic evidence, video evidence, or why doesn't he produce an alien for an interview? They won't do that. Uh, these spy chiefs that trust spies, they have a sense of humor. They have a sense of humor, and it's fun to throw in a few stories to to get the media buzzing. So my take on this is very simple. As long as there is no evidence, I will not believe it. That's how it works. If you make an extraordinary claim, you have to produce evidence, extraordinary evidence. For any claim to be taken seriously, there has to be evidence to back up the claim. Show me the evidence. I have yet to see evidence. I would be the happiest person in the world if alien contact is proven or it happens. I'll be the happiest person in the world. I mean, when I was a kid, I was obsessed with aliens and UFOs, and I really wished that this would happen and we would meet other civilizations and establish contact and cultural enrichment or whatever. So yeah, I'll be the happiest person in the world. But yeah, I have never found a single piece of evidence that would convince me. So I am very skeptical, but I'm hopeful. That's my take on this. Ananya says, Pranam, why are all scorpions fluorescent? What a great question. So let's take a look at what she means by this. Let me share my screen. Scorpions fluorescent. One second. Fluorescence. So scorpions are creatures, as you know, they are very scary creatures. They have this uh, stinger, as you can see. One second, let me share my screen. Where is it? Here you are. So the scorpions, we know what they are, right? So they glow in the moonlight, and they glow in ultraviolet light. So if you go out in the night in a desert or wherever, and you have an ultraviolet torchlight, then you'll be able to detect scorpions very easily, because this is what it looks like. They glow in ultraviolet light and also in moonlight. Moonlight seems to have some kind of ultraviolet component. So this is what it looks like. It's a fascinating phenomenon. And what's even more interesting is that fossilized scorpions and some spiders also, apparently fossilized spiders, also seem to glow in ultraviolet light. Fossils. So the question is, why are all these scorpions, arachnids, scorpions, why are they fluorescent? So they are fluorescent because there is some kind of fluorescent molecule or molecules or compounds that are present in their exoskeleton, on the external part of the body. So I think scorpions, they shed their outer skin every few, I don't know, periodically, I suppose. I don't know what is the period. So the fluorescent molecular compound or compounds, whatever it is present in the exoskeleton of the scorpions. Now, what is the reason why it is so? What is the purpose of this glow? So maybe we don't quite know. It has not been conclusively demonstrated why this sort of evolutionary adaptation has happened, but several theories have been thrown about. For example, it is speculated that possibly this fluorescent molecules or compounds, it protects the scorpions from parasites, perhaps, or maybe it acts as some kind of a sunscreen, or maybe it helps them find mates in the dark or in the light, possibly some kind of such thing. Maybe it has antifungal properties. Maybe it's a kind of sunblock. It protects them from sun. Maybe it confuses the prey of the scorpion and makes the prey easier to catch. Yeah, maybe it makes scorpions easier. Maybe it makes it easier for scorpions to recognize each other. Maybe if they're the same species of scorpion, they have a similar glow, whatever. Yeah, or maybe it's some kind of relic trait from an earlier age in which it was useful. Maybe it's not useful now. We don't quite know. Lots of such theories have been proposed, put forward, but we still don't have the conclusive answer. What we do know is that this is a fascinating phenomenon, and there are I cannot think of any other species of animal or creature or whatever life form that has this very interesting evolutionary adaptation. So that's what I can say. They do fluoresce. The fluorescence is caused by uh, maybe some kind of molecule or molecules or compounds, and we don't know quite what the purpose is. So that's what I can tell you about this. Alpha Beta says, why are octopuses, octopi, so fascinating? Probably better than humans in some scenarios. Do they have extraterrestrial origin? Okay, let's bring the octopus on the screen. Octopus, Octopus. Let me Google that and put octopuses on the screen. What do they look like? This is what octopuses look like. Yeah, this is how they are picturized in cartoons, but the real octopuses, octopi come in a variety of species, in variety of sizes. People even eat them. Yeah, in Japan, in Spain, and various other cultures. Yes, it's a delicacy. And octopuses are very strange creatures. They have eight arms or eight legs, whatever you want to call them. They've got these very interesting looking eyes, and they are very intelligent creatures. They come in very small sizes and large sizes as well. There are like very massive, large octopuses as well, certain species, and so on. So, what makes these creatures fascinating? Do they have alien origin? First of all, no, they do not have extraterrestrial origin, but they are very strange, alien-looking creatures. Deep, they live in the oceans, in the seas. I don't think there are any freshwater octopuses, as far as I know. So, what are the interesting things about octopuses? First of all, the number of neurons an octopus has is approximately the same as the number of neurons that a dog has. That kind of tells you that the octopus is a very intelligent creature. It could have the same kind of intelligence that a dog has. And as we know, dogs are very intelligent creatures, right? Octopuses, and the interesting thing is that the octopus essentially has nine different brains. Each of its arms has what you could call its own brain. The creature also has a central brain which is located in the head region. Yeah, and the central brain is able to uh, overall control the various arms, but the arms also have an autonomous component. They can operate autonomously in certain cases. So this creature essentially has a distributed brain, or what you could even regard as nine different brains. That's one thing. And octopuses are most likely able to recognize human faces. They're very intelligent. They can tell one human being from another, and they can develop likes and dislikes towards different people. Some people they will like very much. Some people they will dislike based on various behaviors that people have exhibited and so on. That sort of thing. And octopuses are they they kind of are known to pull pranks on people. So there was this interesting story that came out of a research lab or aquarium or something. There was an octopus in a tank, right? An octopus inside a tank, and there was in a room, and there was another tank in the room which contained fish. Now, what happened is that the fish were disappearing over a period of several days, and nobody understood where the fish were going because the fish are in one tank, the octopus is in a different tank. Now what these people did is that they put a security camera in the room and they left it on. The next day when they came, they discovered that the octopus was going out of it, was opening the lid of its tank, going outside, walking on the floor, climbing up and opening the lid of the tank that contained the fish, going inside, catching a fish, eating it, then going out of the tank, closing the lid, and climbing back into its tank. And he was hiding the evidence of what he did or she did, whatever, right? So that's the kind of incredibly intelligent behavior that octopuses exhibit, right? So these are some of the interesting characteristics that octopuses have. Very intelligent animals. The kind of intelligence they have is similar to that of dogs. The most intelligent animals, non-human animals that we know of, are dolphins and dogs and cats. Obviously, dogs are said to be more intelligent, and we also could consider crows and parrots to be quite intelligent. These animals, they exhibit tool making or tool using behavior. So even octopuses have been observed to use tools. They use shells, seashells, as tools. They collect seashells and stack them together and use them again as defenses against other organisms, other creatures, or as in order to break the currents of the ocean. They even use coconut shells for various purposes. They collect them, stack them together. So they have been observed in this sort of exhibiting this sort of behavior, tool collection and tool use. So overall, very interesting creature. Looks very alien. It's very different from anything we would typically observe or interact with. And yeah, so that's what it is. And they have a very strange blood. I think it's we humans and most animals, mammals, lizards, etc., reptiles, etc., our blood contains hemoglobin. In the case of octopuses, their blood contains hemocyanin, which is essentially blue. Our blood is red, their blood is bluish or whitish. So lots of differences. Very alien looking creature. So that's why octopuses are so fascinating, and they are the subject of study. Very interesting creatures and very little understood. Very intelligent. So that's why they are fascinating. I'm not sure if they're better or worse than humans. I mean, how do you qualitatively compare two such different species? What is the criterion for being better or worse? I'm not sure. So I would not say it's better or worse, but it's really fascinating, very intelligent, and yeah. So intelligent and interesting species of animal. Okay, Aditya Narayan Pandey says, I think Mars's ice will automatically melt in the upcoming 100 to 200 years, since the sun is slowly becoming a red giant because of conversion of hydrogen into helium. And due to this, many unknown creatures may come back in survival mode on Mars. Maybe humans till that time would have left the Earth, or human race would have come to an end due to unbearable temperature of upgraded version of the sun red giant, and then unknown creatures come alive on Mars. So in 100 or 200 years, the sun is going to become a red giant. This really hurts my feelings. Li- Listen, the sun is not going to become a red giant in the next couple of centuries. It's going to take 5 billion years. 5 with 9 zeros after it. All right? It's not going to happen next week or next year or next century. In 200 years, it's not going to be the end of the solar system. Please understand. These are very large time scales we are talking about. Our sun is about 5 billion years old. It's got another 5 billion years left in it, right? And yeah, so this is not going to happen in the next 100 to 200 years. Yeah, it will eventually become a red giant. It will eventually die a slow, lingering kind of demise. Its outer layers will just waft off into outer space. It's going to give rise to what's called incorrectly a planetary nebula, something like um, I can't think of the names right now, but yeah, the one of the recent images of the JWST shows what's called a planetary nebula. And eventually, what will be left at the core of the sun is what's called a white dwarf. So that's what's going to happen. That's going to happen over a very long period of time, 5 billion years, right? So not a couple of centuries, no sir, no sir. Um, and the process is quite complicated, and you could simplify it, but I've done that multiple times. I'm not going to go into that right now, how it happens. And now what you're talking about, unknown creatures, survival mode on Mars. I mean, we don't have any evidence of any life on Mars. There could have been life in the past, no doubt about it. Mars was a very nice, wet planet, very similar to what the Earth is. That was about about 4 billion years before today, right? And then things happened and things changed, and it became a dry, barren planet. So we know there is ice on Mars, there is subsurface water most likely on Mars, but there is no evidence of life. But the main point I would like to make is that the sun is not going to become a red giant in 200 years. It's going to take 5 billion or so years. It will start in a billion years or so. It will start expanding and all that. But there is plenty of time left. Plenty of time. All right. Okay, since we're talking about Mars, Crazy Brain says everyone is eyeing to go to Mars. You mentioned that if somehow we're able to heat up and melt the remaining ice on the planet, then maybe a hospitable environment can be created. My question is, if the core itself of Mars has cooled down and doesn't have a magnetic field, how can a hospitable atmosphere be created by melting ice? All right. So you are correct. Mars does not have a strong magnetic field. It has a very weak remnant of what used to be a good magnetic field. So the Earth, our planet, has a strong, reasonably strong magnetic field. Why does it have it? It's because of the dynamo effect that is caused by the interior of the Earth. What does the interior of the Earth look like? Let me see. Let me put that on the screen. The interior part of the Earth. So the Earth, the interior of the Earth is something like this, right? The various layers of the Earth. So at the very center of the Earth and in the interior layers of the Earth, so we have the crust and the mantle, yeah, the stiffer mantle, etc. Then you have the outer core of the Earth, which is liquid, and the inner core, which is solid. And there's a magma layer and all that. So the outer core is liquid metal. It's mostly iron and possibly nickel and some other. It's a mixture of metals, mostly iron, and the inner core is solid. So when you have a massive core made up of molten metal, which is hot and which is flowing, the flowing metal conducts electricity, and the moving charges create a magnetic field because of the dynamo effect. Very simple college level, school level, high school level physics, I suppose. Right? So that is why the Earth has a magnetic field. Now, why is the interior of the Earth so hot and molten and all that? It's because of the heat left over from the formation of the solar system. Everything was shockingly hot at the time, right? And the Earth formed out of a molten ball of molten rock and metal and all that. The heaviest parts moved to the center. That's why it's got a metallic center. And the heat is still very much present in the interior of the Earth, which is the heat left over from the formation of the solar system. And much of the heat inside the Earth is also produced by radioactivity and things like that. Let's not go into that. So the Earth has a molten core and a solid inner core, and that's why there's a magnetic field. In the case of Mars, Mars is a much smaller planet. It cooled down very rapidly compared to the Earth, which is still very hot inside. And because it cooled down and the core of the planet became solid, so there are no more moving charges, and that's why the magnetic field died out. Right? So the planet doesn't have anything like the magnetic field of the Earth. Now, why is the magnetic field important? The Earth's magnetic field, let us take a look at that. Earth's magnetic field. Earth's magnetic field. So the Earth's magnetic field, what it does is that it deflects away the solar wind. What is the solar wind? Okay. What is the solar wind? The solar wind is this big wind of plasma that comes from the sun. The sun emits plasma, and that is what we call the solar wind. This is what it looks like, kind of the representation of that. And this solar wind is essentially protons, neutrons, uh, helium nuclei, and so on. Is there a problem with the image? One second, let me see. Give me a second to fix that. It looks like there is a problem with the image, with the connection. Hopefully it's fine. No, it's not fine yet. Please give me a minute. Let me try to fix this issue. It's a little blurred. Some people are saying that is not great. Hopefully it should be fine now. Can you guys tell me if you are able to see me fine, or is it still blurred? There is a bit of lag. Is it blurring? Can you all see me? I think it's fine now. All right. Okay, so apologies for that little problem. So the solar wind is this wind of plasma that comes from the sun. It is a bunch of particles, protons, neutrons, uh, helium, nuclei, etc. And what this does is that it is very dangerous. It can strip away the atmosphere of a planet, which is not protected by a magnetic field. So, in the case of the Earth, the magnetic field of the Earth deflects away this plasma, the solar wind. And one of the effects of that is that we see auroras, right? Auroras in the North Pole region and the South Pole region. But the atmosphere is protected from the solar wind because of the magnetic field of the Earth, which acts as a shield of sorts. In the case of Mars, the magnetic field isn't there, and therefore the solar wind directly bombards the atmosphere of Mars. And because of this, the atmosphere of Mars slowly was stripped away. And that's why Mars has a very thin atmosphere today. It's got a very thin, tenuous kind of atmosphere, much thinner than that of Earth. It still does have an atmosphere, but it's nowhere like the kind of atmosphere that we have on the Earth. And that is why Mars lost all its water and all of it. It became a very dry and arid planet. It's got water under the surface and so on. So that's the reason why it is that way. Now, the thing is, if we are able to somehow heat up the planet, let's say we construct an array of mirrors, gigantic mirrors around the planet, not completely around the planet. It will not envelop the planet entirely, but this array of mirrors will focus more sunlight on the surface. That could heat up the planet. It could melt the ice, and it could create this water vapor and all that. It could change the atmosphere of the planet, make the atmosphere thicker and so on. And that's the process of terraforming. Or maybe you could nuke the poles, like some people say, and that could do the thing. So, yeah, you could create over time a more hospitable environment, a thicker atmosphere over time. It could take maybe 1,000 years. So the question is, the core of the planet has cooled down. There is no magnetic field. Then how can you sustain also a hospitable atmosphere? The thing is this: you can sustain a thick atmosphere for a few million years, maybe 10 million years, maybe 100 million years. The effect of the solar wind on the atmosphere, of stripping away the atmosphere, is a slow process. It doesn't happen in a week or a month or a year or even a century. It may take a few million years. So if you can create a thick atmosphere at a fast rate, then you could have a nice, hospitable, habitable planet. And this scenario will last for a few million years, maybe a million years, maybe 10, maybe 100, which is perfectly great for us. Our species is at most a quarter or a third of a million years old. So for us, a million years is like forever. So, so we have to look at the time scales and put that into the right context and perspective, right? So it won't last forever. We know that, but it will probably last longer than how than the age of our species thus far. So which is perfectly good for us. So that's why we talk about doing this, but we are still very far from doing that. We still don't have the technology to, first of all, reach there in sufficient numbers, and secondly, to terraform the planet. So it's all in the future, but it's possible. Okay, Kabir Singh says, what is so special about Homo sapiens? The history of humans on Earth is more than a million years. So why were other species not able to do remarkable advancements like the modern humans? Or is it the mystery? Please answer. So, as far as we know, we are the most intelligent and advanced species that has ever existed on our planet, as far as we know. We have seen the entire fossil record, whatever is available to us, and from all of that, we have concluded that we are the most advanced species that has ever existed on the planet. Now, it's entirely possible, like Joe Rogan would say, that there could have been other civilizations on this planet, maybe 100 million years ago, maybe a half a billion years ago, and we have lost all trace of that because the surface of the planet is geologically active. There is tectonic movement. Yeah, and all that. So what happens is that over time, over millions of years, the entire topology, geology of the earth changes. What is on the surface goes deep underground, and what is deep underground comes to the surface. It's an ever changing environment, an ever changing surface, but the changes happen over very long geological time scales. So if an advanced civilization and advanced species existed maybe 500 million years ago, it's entirely possible that there would be no trace left of that. Whatever traces exist would have been buried deep, 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 kilometers underground, and we may never ever find that. So that is one possibility, right? That such a species, other species may have existed, but we have lost all traces of that. Now, but as far as we know, from all the evidence that we have discovered thus far, we are the most advanced species. So the question is, what is so special about Homo sapiens? What makes us special? The history of humans on Earth is more than a million years. Well, if you take the entire uh, lineage of archaic humans, proto-humans, etc., yeah, it's about 2 million years. Uh, our our ancestors, they split off from the ancestors of the chimpanzees about, I think, about 2 million years before today. And the common ancestors of humans and chimpanzees split off from the ancestors of gorillas, I believe, about 6 million years before today. 60 lakh. Yeah. So it's not a very long period of time. So what makes humans special, right? The first thing that makes humans special is opposing thumbs. You see, opposing thumbs. Uh, we can pinch each of our fingers in this manner with our thumbs. There is no other species of, well, monkeys can do it. So that is what makes the monkeys, the primates, different from other species, right? This property. No, apart from primates, apart from monkeys, no other group of animals has this property to be able to pinch like this. So this gave humans and monkeys the ability, the dexterity to create tools and to manipulate their environment in a variety of ways that other animals can't do. I mean, if a dog has an itch on his back, he cannot reach around and scratch himself, can he? He has to go and scratch his back against a tree or something. Um, so that's one thing. The second thing is bipedalism. For some reason, humans became bipedal animals. It's extremely unnatural to walk on 2 feet. All animals, most animals, walk on four legs, right? Dogs, cats, bears. Um, Bears are a special kind of dog. I mean, look at the face of a bear. It looks like that of a dog, right? So a bear is like a massive dog, and bears actually can walk on 2 legs if they want to, when they feel like. But typically, if you see bears running and walking and ambling around, they do it on 4 legs. And bears also have a certain amount of dexterity and intelligence. So the thing is this: when you walk on 2 legs, when you walk upright, your head, your face, your eyes are much higher up from the ground, and you can see much further away. Right? If you can see much further away, your brain, your mind has to process much more information. And that, in a way, could induce your brain to develop more, your cranial capacity to increase. And that obviously is something that gives rise to higher intelligence. Of course, one can find other examples like giraffes that have not developed higher intelligence, but giraffes don't have opposing thumbs. So the ability to create tools, the ability to be extremely dexterous with your hands, the ability to see far away, the ability to do walk upright, these are things. And then you have the spectroscopic vision. If you see birds, eagles, etc., if you see dogs, cats, not dogs and cats, but birds, for instance, they have eyes on the sides of the heads. Fish have eyes on the sides of the heads. So they cannot see in 3D. Humans have eyes right here. So we can see in depth 3D. So a multitude of factors came together and created this perfect storm that gave rise to the intelligent apes in suits. There are humans. We are genetically extremely close, extremely similar to chimpanzees and gorillas, and bonobos as well. Extremely close. The genetic difference between humans and chimpanzees is about 1%. 99% approximately, roughly, of our genes are the same, and yet we are so different. We are far more intelligent. Apart from that, physically we are extremely unremarkable. You could be 6 feet tall, you could be a bodybuilder, you could be Arnold Schwarzenegger, and yet a chimpanzee who is half your size is physically going to be stronger than you. So humans are incredibly weak as animals. We can't run fast. Dogs, cats can run faster than us. Chimpanzees can run faster than us. Bears can run faster than us, who are so large and fat. Humans are incredibly weak, and yet the superpower we have is our intelligence. We are the apex predator in our planet. We are the super predator, the most dangerous animal that exists, and we have taken over the planet, haven't we? So these are the things that make Homo sapiens special and different from all others. So that's what it is. It's a whole combination of factors that came together to produce this remarkably intelligent and extremely dangerous species. Ananya says, as such, plants look passive, but we know that they have life. Do they also have their own sensory system designed to respond to danger or other changes in their environment? Do plants talk to each other? Pranam. All right. Plants obviously are living beings. We know that for sure. Plants grow, plants die, plants have life cycles, and so on. Plants are living beings. We know that. They do respond to external stimuli, not in real time as we do. Plants don't have muscles. They have their own uh, internal systems. They have sap, they have parenchyma, they have chlorenchyma, they have a whole. It's botany. We are zoology, they are botany, right? Plants do respond to changes in the exterior environment. They do respond to stimuli. So if you see sunflowers, for instance, sunflowers typically face the sun. As the sun moves through the sky over a 12 hour or so period, the sunflower moves. It kind of tracks the sun. You see plants, when it's night, their leaves close down. When it's daytime, they can sense the light has come out and the leaves open up, right? You can see that. Um, in a forest, if you see a time lapse, you will see that trees try to stay out of each other's personal zones. They all try to keep some distance between each other. uh, that sort of movement you can see, and so on. So plants definitely do respond to external stimuli. If a plant is under attack from some predator, they have defense mechanisms that get activated when some part of the plant is eaten up, right? If, let's say, you have a plant which has a certain kind of defense mechanism, and some animal, a grazing animal, comes and starts chomping on it, then it will activate that defense mechanism, and some sort of response will be seen. So plants do respond to the external environment. They do seem to have some kind of sensory system, not the kind of sensory system that we have. I'm not sure if they feel pain. They don't even have a central nervous system or such. So the concept of pain most likely doesn't exist with plants. But they do respond. Uh, they do perceive threats and respond accordingly, and so on. I don't know if plants can communicate with each other. For communication, you need intelligence. For communication, you need a brain, a central nervous system. Plants don't have anything like that. They have a distributed system of sensory inputs and all. So it doesn't appear like plants talk to each other. There have been experiments done about the response of plants to music. You play horrible, noisy sounds to plants, they don't grow very well over a period of weeks. If you play pleasant music to them, they grow better. So yeah, there is something out there we don't quite know yet, and that's one of the mystery, right? That's a big mystery. uh, there is so much that science doesn't understand. Clearly there is some kind of relationship between the kind of sounds that you expose a plant to and the way the plant grows. And somehow nice melodious music makes plants grow better and healthier. So there is something there, but we don't quite know what it is. That's the mystery. Okay, Sarthak says, we know that when a particle of antimatter and matter comes together, they completely annihilate each other. But what about the neutrons in both particles? Are the neutrons of an anti-oxygen atom the same as the neutrons of a normal oxygen atom? If yes, then do they still annihilate each other? This is an extremely good question, very intelligent question. So, like I have explained in the past, antimatter is the difference between antimatter and matter is that certain properties in antimatter are the opposite. For instance, the regular proton has an antimatter counterpart, the antiproton. Now, the regular proton is positively charged, the antiproton is negatively charged. The electron has an antimatter particle, antimatter antimatter counterpart called the positron. The regular electron is negatively charged, the positron is positively charged, but it has the same mass. So proton, antiproton, electron, positron. What about the neutron? The neutron has no charge. So does it mean? And we know that the photon is its own antiparticle. The photon is a different thing. It's a boson. Um, so what about the neutron? The neutron is neutral. So is the neutron its own antiparticle? No, not quite so. The neutron's antiparticle is the anti-neutron, the antineutron. Now, what is the difference? The difference is the quark composition of the neutron and the antineutron. So, in the case of the neutron, you have one up quark and two down quarks. UDD is the quark composition of a neutron. In the case of an anti-neutron, you have three anti-quarks: U bar, D bar, D bar. Anti-up quark, anti-down quark, and anti-down quark. It's a triplet of quarks. So that is the difference. A neutron is made up of regular quarks, an anti-neutron is made up of anti-quarks. That is the difference. But yes, both are neutrally charged. They don't have any electric charge. And if they come into contact with each other, they will instantaneously annihilate each other. So it's a good question. So you need to dig deeper when it comes to neutrons and antineutrons. It's just not just the charges, it's the quark composition. And antineutrons have antiquarks. Apart from that, they look just the same as regular neutrons. But you bring them together, neutron, antineutron, they will annihilate each other into pure energy. Excellent question. Okay. Rajat says, in the Schrödinger equation, there is a presence of the imaginary, the I, right? Square root of -1. Why is it so? Does it mean that the quantum nature can only be defined by complex numbers? Please shed some light. This is a very good question. So let me try and explain what is the meaning of all of this. So you may know, hopefully, that the Schrödinger equation is a wave equation. It describes a wave. What kind of wave? Probability wave. The probability of a particle being in a certain place at a certain time, in the TDSE, time dependent Schrödinger equation. So the probability of a particle being found in a certain place, and the whole that is the probability, and the whole set of probabilities is the whole Schrödinger equation. It's a wave equation. It's a wave. Now, what is a wave? Think about a sine wave. A sine wave looks like that, right? It's a sine wave. And any wave can be thought of as a superposition of a variety of sine waves and cosine waves. You put them together in a superposition, you get any kind of wave. You can create any kind of wave or any kind of shape from a superposition of sines and cosines, sine waves and cosine waves of different amplitudes and frequencies and all of that. Now, have you heard of the Euler identity, EULER? One of the ways of looking at it is like this. Let me share my screen, and let's take a look at this. So you can represent sines and cosines in this manner. The cosine of x is the real part of e raised to ix, which is e raised to ix plus e raised to minus ix divided by 2. And the sign of x is the imaginary part of e raised to ix, which is e raised to ix minus e raised to minus ix upon 2I, right? Now we know that sines and cosines are very much real. It's not imaginary, but it can be represented in this manner. It's a more and it all comes out of the complex plane, which is represented like this, and you can see why e raised to I theta is cos theta plus I sine theta. So there is a variety of ways of representing sines and cosines. One of the ways of doing it is through by using imaginary numbers, and that is kind of the reason why there is the I in the Schrödinger equation. The Schrödinger equation is a wave equation, and in wave equation, in any kind of wave equation, you can always have imaginary numbers. It doesn't mean that it's an imaginary equation. Of course, you need to take the modulus to get an actual result and so on. But so I hope that explains why it is so. It's because it's a wave equation, and waves can be represented as sines and cosines or a superposition of sines and cosines. And when you have sines and cosines, you can have the I square root of minus 1 in the mathematical formulation. So that should kind of give you some kind of idea as to why the Schrödinger equation has the I. That's not the exact answer, but it's an analog kind of analogy to help you understand why it is so. To understand why the equation is the way it is, you need to see how it is derived, which is a whole different story. I'll not go into that right now. But think of it this way, and it will help you understand why there is the I in there. Right, let's go next question. Shreya Jain says, how can we make ballistic missiles maneuver just like hypersonic missiles? All right, hypersonic missiles. So first of all, let's talk about what a hypersonic missile is. What's a hypersonic missile? What is the speed of sound? The speed of sound is 343 meters per second. Yeah, 0.34 kilometers per second. Yeah, that is the speed of sound. An intercontinental ballistic missile, ICBM, has a speed of about Mach 20, Mach 21. What is Mach 1? Mach 1 is the speed of sound, which is 0.34 kilometers per second. ICBM, intercontinental ballistic missile, travels at, let's say, Mach 20 times the speed of sound. That's how incredibly fast it goes. Now, when we talk about supersonic, hypersonic, supersonic speed is from Mach 1.2 to Mach 5, which is 1.2 times the speed of sound to about 5 times the speed of sound. That is the supersonic range. Hypersonic is between Mach 5 and Mach 10, 5 times to 10 times the speed of sound. High hypersonic is between Mach 10 and Mach 25, and then there is re-entry speed, which is more than Mach 25, which is when you have missile re-entry or re-entry of spacecraft into the Earth's atmosphere. So these are the different speed ranges. So when we talking about hypersonic, it's typically between Mach 5 and Mach 10. ICBMs are in the high hypersonic range. Now the question is, how do we make ballistic missiles maneuver like hypersonic missiles? Well, I suppose you're talking about cruise missiles. In the case of various cruise missiles, let's say you have the BrahMos, which is a supersonic missile. It is a missile that can maneuver and evade countermeasures. You also have other kinds of hypersonic missiles which have maneuverable characteristics, right? So how do we make ballistic missiles maneuver? So there is something called a maneuverable re-entry vehicle, MARV. Before we talk about MARV, let's talk about MIRV, multiple independently targetable re-entry vehicles, MIRV. So when you have a ballistic missile, you can put multiple warheads in that missile, and when it re-enters the atmosphere after its parabolic trajectory, which takes it out of the atmosphere, when it re-enters the atmosphere, you can make each of these warheads go in independent directions. So a single missile can deliver, let's say, 10 warheads to 10 different locations, which makes it very hard to intercept, right? So a number of MIRV equipped missiles exist, like in India we have the Agni P, which was tested, I think, in 21 last year. It was tested, I believe, with two warheads. And those were not just MIRV warheads, those were MARV warheads, maneuverable re-entry vehicle, which means that these individual warheads were capable of maneuvering, not just going straight down, but maneuvering and evading countermeasures. So that's the MARV technology. And these maneuverable warheads will have certain control surfaces, right, that can allow them, which is like fins or like small winglets which you see on missiles, which allow them to go in different directions and eventually reach the target in a way that is not predictable by the countermeasures system or the missile defense system. So this technology already exists, right? So that is the MARV technology. You also have hypersonic glide vehicles, which use boost glide trajectories. It kind of doubles the range over the purely ballistic missile trajectory. There is something called skip glide and skip re-entry, etc., which could extend the range of the missile even more. It makes the path of the missile very unpredictable. You don't quite know where it's going to come from, and once it re-enters from some angle that you don't expect, after that it may even maneuver further before it reaches the target. So it makes it extremely difficult for any missile defense system to intercept that missile. So there is a Russian hypersonic glide vehicle called the Avangard, which is already deployed. Then you have Chinese uh, hypersonic glide vehicles called like the DFZF, I think it's called, or it was called the WU-14 or something, a Chinese hypersonic glide vehicle. India is also testing such technologies. So India now has MIRV technology, MARV technology. The Agni P has been tested with that. The Agni 5, the Agni 6 most likely also has this capability, and so does the K5, K6, a system of family of missiles and so on. So that's what we do. So these are different classes of weapons, and these are in the high hypersonic range, right? When you talk about hypersonic missiles, you most likely talking about cruise missiles, like the Zircon cruise missile or the next generation BrahMos missile or whatever. Those are in the hypersonic range. Ballistic missiles and re-entry vehicles, etc., are in the high hypersonic range, extremely high speeds, Mach 20 or maybe slightly more than that. So that is how it is done. It's a very interesting field of aerodynamics, not very technically well. Technically, it's simple enough, but to make it work, it's really hard. So you have a whole family of technologies that go into making this work, and it's you need a lot of testing, as with any technology. Okay, next question. Karthik Srinivas says, could the universe be flat? Could the universe be flat? So what do we mean by flat? The universe is three-dimensional, four-dimensional if you look at general relativity. So what does it mean when you say the universe is flat? Let's say I have a book. It is flat. We know it's flat. It's two-dimensional. Its surface is two-dimensional. It is flat. But what do we mean by the flatness of the universe? Doesn't make any sense. Think about it like this. Think of, okay, let me show an image. It's always better to show images to make sense of things. Okay, so we talk about different shapes of the universe. Now you see this, it makes a little bit of sense. And yet we know that the universe is four-dimensional. It has got four dimensions, three dimensions of space and one dimension of time. Four dimensions. But this is an analogy. So we know from general relativity that the presence of mass curves space-time. Forget about the fourth dimension, time, for now. Think about the three dimensions of space, right? So when you have mass, it curves space-time. So if you shine a ray of light, that ray of light will not travel in a straight line, it will travel in a curved path, right? So let's say you have, take a look at the topmost image where it says flat. Let's say you have a triangle, and each side of this triangle is, let's say, 100 light years long. A light year is a distance, is a unit of distance. The amount of distance a light ray a photon travels in a year. So let's say each arm of this triangle is, let's say, 100 light years long, and you have three spacecraft at each corner of the triangle. Now, let's say these spacecraft that they shine light beams or laser beams at each other, and that is what creates this red triangle. If there is mass present in the space, then these beams of light will not be straight, they will be curved. And in the real universe, you have this curvature in space. So if you look at the universe at small scales, 10 light years, 100 light years, 1000 light years, there is a lot of curvature, right? And the universe is not flat because light doesn't travel in straight lines at small distances. But if you travel very large distances, parsecs, kiloparsecs, megaparsecs, the universe looks remarkably flat. At small distances, light travels in curved lines, but at very, very, very large distances, light travels reasonably flat. Right? Light travels in a straight line. So the universe appears to be flat. Now, what do you mean by flatness? Uh, One of the simple ways of looking at flatness and curvature is this. In a positively curved topology, like the one you see down here, the one you see down here, the- in a curved topology, let me give you a different analogy. Let's say you are on the surface of the earth. All right, let me share the map, even though we are doing science today. So here we are. This is the planet. Let's say you are sitting on the equator at Gabon, and you start going, and let's say you have built a bridge along the entire equator of the planet, and you start walking, or you start going on a plane or on a train or whatever eastwards. You start from Gabon on the equator, you keep going eastwards, you reach Indonesia, you keep going further east, keep going further east, you go to Ecuador, you cross South America, and you will eventually end up in the same place, because the surface of the earth is not flat, it is curved. Right, the surface of the earth is curved. Now we know from geometry that when you have a triangle, the sum of the interior angles of a triangle is 360 degrees. Yes, the sum of the interior angles of a triangle is 360 degrees, but that only works in flat space. If you make a triangle, if you draw a triangle on the surface of the earth, you will find that the sum of the angles, interior angles of the triangle, is going to exceed 360 degrees. So that is curved space. All right. Now let us come back to the diagram that we had. Here we are. So on a curved surface, you will find that the sum of the interior angles of the triangle is going to exceed 360 degrees. In a negatively curved topology, you will find that the sum of the angles is going to be less than 360 degrees, and only in a flat topology it is exactly equal to 360 degrees. Let's take a different look at this. In flat space where there is no curvature, parallel lines remain apart all the way to infinity. In positive curvature, parallel lines converge. They will eventually converge together, they will meet. And in negative curvature, parallel lines will diverge from each other, right? So this is something we can test in the universe. You can actually test it, and what we find is that the universe, or very large uh, regions of space, is completely flat. There is no curvature. That's what we find. That is what we have discovered thus far. The universe seems to be remarkably flat, which seems to indicate that the universe could be infinite in size. Because if there was curvature, it means that the universe has a finite size. No matter how small the curvature is, if there is any amount of curvature, it means it could be spherical and it may have a finite size. But since it is completely flat, from whatever we have seen, it could indicate that the universe is infinite. It never ends. So, our means of measuring all these different things is our means are very rudimentary. We are a very technologically primitive species. We are monkeys wearing suits. That's all we are. And we know next to nothing about the universe. We know less than 5% of the universe. So we should not get carried away and think that we know now everything and the universe is infinite. From what we have observed thus far, in the past few decades, we have observed that the universe appears to be remarkably flat. It could be something else. We don't know. Maybe it's a local effect only in the visible universe. Maybe there's something else out there which we're not able to see, and maybe there is curvature there. We don't know. We don't quite know. We know very little about the mysteries of the universe. But from what we have observed, the universe appears to be flat thus far. Let's see how it goes. Okay, Naman Gupta says, we can see stars in the sky with our naked eyes, but not galaxies when they are millions of times bigger. Why is this so? Or is it that we can only see stars within our galaxy with the naked eye? So when we look at the sky, the stars that we see are the stars that are present in our galaxy, right? And galaxies are not millions of times bigger than a star. They are billions, hundreds of billions of times bigger than stars. But they are incredibly far away. The closest, the nearest galaxy to the Earth, the Andromeda galaxy, is about, I don't know, 1.5 million light years away from here. That is astonishingly far away. And yet it is visible, actually. Let's take a look at Andromeda night sky. 1 second. Let's see what the Andromeda galaxy looks like in the night sky. It's actually visible. Let me share my screen and show you what it looks like. Take a look at this. So this is what the night sky would look like if the Andromeda galaxy were brighter. The galaxy is quite faint. It's not quite visible like this. If you make it brighter, then it will be actually visible like this. You can see the moon and you can see Andromeda, which is actually larger as seen from the Earth than the moon, right? But it's so far away that it's quite faint, and that's why it looks like a smudgy blob. It's not quite visible, but this is the effect. If it were not so dim, it would look like this. Now, when it comes to other galaxies, which are much, much further away, they are so far away that they look like points to us. They look like points. It's because of the enormous distances involved that the galaxies look so small. So when we look at the sky, it looks like it's just stars, but many of these stars could actually end up being galaxies, and that's what we discover when you take a telescope and look at the sky and magnify various objects, and then these little points resolve into galaxies. So we do see galaxies, but they look like points, except for one or two, like the Andromeda galaxy. The Andromeda galaxy looks like a fuzzy, cottony, little smudged out blob, but is actually a galaxy, right? So it's because of the enormous distances involved. And the Andromeda galaxy is so far away, 1.5 million light years away, I think, yeah, that it's quite faint. So even though it is visible as a disk, as a side-on disk, it's quite faint. So we can't really tell that it's a galaxy. You make it brighter using various techniques, it looks like a proper galaxy. Eventually, it's going to merge with our galaxy. So in the future, it's going to be much closer, and it will look much larger and much brighter in the future. And the thing is, even our galaxy, we don't quite see it, right? We have so much light pollution in the cities on the surface of the Earth that we don't quite see our own galaxy, even though we are in the middle of it. You go in the middle of a forest where there are no artificial lights, you can see the entire Milky Way side on. It's incredible. So these are the reasons why we don't quite see these things. Okay, Vega says, what does collapsing under one's own gravity mean? Can you explain this in layman's terms? All right. Layman's terms. I try to explain everything in layman's terms, actually. What does collapsing under one's own gravity mean? So when you talk about collapsing under one's own gravity, we're not talking about human beings. We typically use this kind of language when we talk about stars. We talk about stars collapsing under their own gravity. What does that mean? Let's say you have a star that is, let's say 20 times the mass of the sun. When you have a star of that size, it's going to, every star is a star because it there is a fusion reaction going on inside it. A star is incredibly massive. What is the mass of the sun? Let me take a look at the mass of the sun. Sun mass. Solar mass is 10 raised to 30 kilograms, right? No, it's 10 raised to 24 kilograms, 30, yeah, something like that. It's enormously massive, right? And this enormous mass of the sun creates a ridiculous amount of pressure in the inside of the sun. Now, the star is mostly made up of hydrogen gas, hydrogen, and this pressure. So, if you go to the bottom of the oceans in the earth, there is an incredible amount of pressure from the water that's on top of you. If you go to the bottom of the Mariana Trench in the Philippines region, there is more than 11 or so kilometers of water above you, and that exerts an enormous amount of pressure or anything which is down there. You take a regular submarine there, it's going to get crushed like a can of Coke. Yeah. So if that is the pressure of water, imagine the enormous pressure of the sun on the interior of the sun. And this enormous pressure causes atoms of hydrogen to fuse together into helium. And that is the nuclear reaction that produces this enormous amount of light and heat, which keeps us alive here on the earth, right? So that is what fuels the nuclear reaction, the fusion reaction. So there is gravity, there is enormous pressure, and yet the star doesn't collapse into a point. Why is that so? Because of something called the Pauli exclusion principle, which is a quantum mechanical principle. I will not go into that layman's language. What it says is that fermions, a certain kind of particle, protons, neutrons, electrons, they cannot occupy the same space, right? And you try to squeeze them together, they're going to push back, and that is what causes this outward pressure that resists the inward collapse of a star. That's why a star remains circular and it has a certain size. It doesn't collapse into itself, right? Because of the Pauli exclusion principle, and also because of the nuclear reaction that produces this outward effect, this outward pressure. So there's a balance, an equilibrium that causes a star to have a certain size. Now, when you have a star that exceeds a certain size, let's say it's more than 20 times the mass of the sun, eventually all the hydrogen in the star will be used up. It will become helium. Then the helium atoms will start fusing together, and you will have the formation of heavier and heavier elements. And all of these fusion reactions give off energy. Now, eventually, what happens is that the star will run out of heavier elements. It will start fusing iron. Iron will start being produced in the interior of the star. And the fusion reaction that produces iron consumes more in energy than it gives off. Right? And therefore, this heat source disappears. The, the energy, the outward pressure that resists the inward collapse of the star suddenly goes away. The moment iron starts forming inside a star, the star collapses upon itself. It's a very rapid collapse. So it will collapse upon itself. And if the mass of the star exceeds a certain limit, let's say more than 20 times, I'm just giving a rough ballpark figure. If it exceeds more than 20 times the mass of the sun, let's say, then nothing will be able to eventually stop the collapse of the star upon itself. Not even the Pauli exclusion principle, not even the neutron degeneracy pressure that you see in neutron stars. It will simply collapse, keep on collapsing until it becomes a point, what's called a singularity in general relativity. In other words, the star will wink out and become a black hole. That is what we mean by collapsing under a star collapsing under its own gravity. In the case of the sun, it's not massive enough. So in the case of the sun, eventually what will be left behind after all the fusion reactions is a massive spherical carbon crystal, a massive, very, very hot diamond. It's called a white dwarf. It's going to be very hot for a very long period of time. Eventually, it will cool down, it will stop glowing, it will become a black dwarf. So the sun will not be able to collapse under its own gravity. At the end of its life cycle, it will become a massive ball of diamond, a white dwarf. Larger stars will collapse into neutron stars. Uh, everything is given off, and at the end you have a neutron star at the end of the life cycle. A neutron star is an extremely ultra compact atomic nucleus, essentially just neutrons with a crust of other protons, etc., on the surface. Possibly, we don't quite know, but that's what it's like. So neutron stars also don't collapse under their own gravity, but certain stars, provided they're large enough, do collapse under their own gravity and they become black holes. So that's what we mean by this term, collapsing, a star collapsing under its own gravity. Manmat Tiwari says, I have never been much interested in cosmology, but this one sentence I've heard very often from me, and other astrophysicists: death of a star. When a star dies, blah, blah, blah happens. If a star can die, does it imply that a star is a living entity? If yes, is there a way with which we can communicate with a star? Do stars communicate with each other? Do they have a social media? Please pick this one. I really want to know. Okay. See, it's like this. When a scientist wants to communicate with non-scientists, they cannot use mathematical equations. They cannot use scientific terminology. They have to use analogies. We talk about the evaporation of a black hole. No, black holes don't actually evaporate. It's not water vapor that comes out of it. But we use the term black hole evaporation. And that is a term that we use to communicate mostly with non-scientists, right? And similarly, we use this term, the life and the death of a star. It's not a living entity. It is not life as we know it. It's a nuclear reactor, a fusion reactor, a massive thermonuclear reaction that we are witnessing in real time. Right? That's what a star is. So it's not life and death, but it's just a certain kind of language that scientists use to communicate with non-scientists. Because otherwise people don't get interested if you use it's uninteresting if you use mathematical equations and things like that. In scientific papers and publications, one typically sees different kind of language, right? Even there, scientists would write about life and death, life cycle, etc. It doesn't mean actual life. It's just the overall existence of a star in a certain state, and the transition from one state to another, one phase to another of its existence, right? Existence. So it's just a figure of speech. It doesn't mean that the star is a living being. Yeah. That's something you use for communication, for making communication effective and interesting. If I start using technical language with you and scientific language with you, you guys will all lose interest, obviously, because it will make no sense, right? So that's why we use such terms. It doesn't mean that it's actually alive. But yeah, good question. Okay, Samir says, can we make water artificially by combining hydrogen and oxygen atoms? What is the progress of technology to make artificial water? See, if you combine hydrogen and oxygen, we know the chemical composition of water: H2O, 2 atoms of hydrogen, 1 atom of oxygen. You bring that together, you have H2O, which is water molecules. So that's not artificial water, that's actual water. You can do it. Shall I show you an example of that in action? Let me show you. So hydrogen and oxygen are excellent rocket fuels. Let me show you once again. So let me show you the production of water in this manner. This space shuttle, if you can see it, it's got this orangish tank. This orangish tank used to contain liquefied hydrogen and liquefied oxygen. And the exothermic reaction gave rise to nothing but water. So if you see all of this, what looks like smoke, it's not smoke. Much of it is water vapor. So in the space shuttle, actually, you have two boosters also. These booster engines, these boosters are on the two sides. Those are solid fueled rockets. So those contain some chemical, which I'm not sure what it is. You can look it up. But the space shuttle itself, if you see, it has got three engines. Those engines, they use liquefied hydrogen and liquefied oxygen, and they give off water vapor. Yeah. So that is one of the ways in which you can combine hydrogen and oxygen atoms and produce water vapor, water, in an exothermic reaction. So yes, to answer your question, it can be done. You can make water artificially by taking hydrogen, taking oxygen, maybe liquefied hydrogen, liquefied oxygen, bringing them together, igniting them with a spark, and producing water vapor. It's possible. Why would you do it? Don't we have enough water readily available on the planet? We have abundant re- uh, reserves of water in the oceans. We have a lot of groundwater and rainwater and whatnot. Yeah. Why do we need to do this? It is certainly possible to do it, but what is the need to do it? It is incredibly expensive to produce water in this manner. You have to have liquefied hydrogen, which is extremely difficult to produce, extremely expensive to produce. You need to have pure liquefied oxygen, again incredibly difficult and expensive to produce. You need to maintain them at cryogenic temperatures, very cold temperatures. You have to bring them together explosively, which is a very dangerous thing. Why do that? Why do that? So it can be done, definitely. I just showed you it's done, but it's a very hot exothermic reaction, and there's no need to do that. Just take the water that's available on the planet in incredibly large quantities, in great abundance, and use that. So so that's a more cost effective, efficient, and practical way of acquiring water instead of creating water artificially. Yeah. Karan says, what is archeoastronomy? Archeoastronomy, well, this is, well, yeah, okay. So archeoastronomy is the science of deciphering ancient astronomical data, like thousands of years old. So for instance, let me show you an example of that. Oldest supernova. Let me share my screen. So for instance, there is this rock inscription in northern India. In This is what it looks like. It's This rock inscription was carved on a rock in northern India, in Kashmir, I believe, about 6,000 years ago. And it shows two guys hunting. There's a deer, and there are two suns in the sky, right? Two suns, not one sun, two suns. So, so it was somebody got the bright idea that this may represent a supernova in the night sky. And so scientists in the Tata Institute of Fundamental Research, Mumbai, TIFR Mumbai, they looked it up. They did some kind of analysis, and they discovered that this represents a supernova that happened about 6,000 years ago. And I don't remember what the name of the supernova is, but you can look it up in this article. It's not two suns; it's the sun, and it is a supernova, which would have appeared as almost as bright as the sun, and that's why it was drawn in this manner, right? So this is an example of archaeoastronomy, ancient records of astronomical events that are recorded either on rock or in ancient literature, ancient texts. And you take that and you use astronomical calculations using celestial mechanics, etc., and you try to date those events. When did these events happen based on the astronomical data that is embedded in the texts? So that is archaeoastronomy. It can be very accurate provided you translate or interpret the text properly. If you don't interpret it properly, you're going to end up with all kinds of incorrect inferences and so on. And there are certain issues in archaeoastronomy. For instance, when it comes to comets, when there is, let's say, a 3,000-year-old text that says a certain comet was in a certain location in the sky and so on the time. The thing about comets is that their path changes. Comets are they have unstable trajectories because they give off gas when they are heated by the sun, and the gas jets can occur in different directions. And because the jets can occur in random directions, the trajectory, the path of the comet can change. It's unpredictable, so you cannot reliably and accurately use comets for archaeological predictions and analysis and so on. So that, in short, in brief, in a nutshell, is what archaeoastronomy is. Vishal says, what could possibly be in the center of our universe? Are there any theories regarding this? The center of the universe, right? So this essentially can be reformulated. This question can be reformulated to ask, where did the Big Bang take place? We know that the universe, the best theory that explains the observable universe is the Big Bang theory, right? The so-called Big Bang theory, which says that the entire universe originated in a singularity, or what was close to a singularity, which expanded outwards in what is called the Big Bang, and that gave rise eventually to the universe that we live in. So many people ask this question, where did the Big Bang take place? Well, it took place everywhere. The entire universe was compressed into an infinitesimally small region of space, into a infinitesimally small point. So everything that's here was inside that, which means when the Big Bang happened, it happened everywhere, which means there is no center of the universe. If you want to think of some place as the center of the universe, it's where you are. You, my dear viewer, are the center of the universe from your perspective. From my perspective, I am the center of the universe, and so on. So every point in the universe, as far as you know, I just spoke about this a few minutes ago, that the universe seems to be remarkably flat, which could indicate that it possibly could be infinite. If you have an infinite universe, it's mostly unlikely, but let's say it's an infinite universe. If it is infinite, then any point in the universe is a center, right? So you could say, and if you look at the observable universe, which is a spherical region of space that we can observe, from our vantage point, we are at the center of the observable universe. So the best answer I can offer you is that you are the center of your universe. I am the center of my universe. And the Earth, our vantage point, is the center, is the actual center of the observable universe. All right? That's not a theory, it's a fact. Ananya says, how would you compare quantum mechanics to Einstein's theory of relativity? Which do you think is more accurate, and what would be a joining bridge between them? Okay, how do you compare these two theories? These are incredibly successful theories, first of all, and extremely accurate. The most accurate, the most successful theory that we do have is quantum field theory, which is an advanced version of quantum mechanics, right? It is second quantization and field quantization and so on. So it is incredibly accurate. And all the technology that we enjoy today is the result of our understanding of the quantum world, the ultra microscopic world from which our physical reality emerges, right? So that is quantum mechanics, quantum field theory. It is the theory of the incredibly small domain, the ultra microscopic world, subatom, atomic and the atoms, nuclei, subatomic particles, protons, neutrons, electrons, quarks, the various fields, and so on. That is quantum mechanics or quantum field theory, the theory of the ultra microscopic universe from which our lived reality emerges. Einstein's theory of relativity is also the theory of the universe on large scales. It's the theory of the large scale universe. You know, so when you talk about quantum theory, it's about ultra microscopic scales. When you talk about relativity, it's large scales, light years, parsecs, megaparsecs, and so on. The very large scale structure of the universe. On those scales, you have Einstein's general theory of relativity, which is curved space-time, geometrodynamics. That's what it is. Four-dimensional space-time. So these two theories are tested, they are proven. Scientists have been trying to disprove them experimentally for decades. Thousands of different kinds of tests have been done, and they have all failed. These theories work, they are valid, but we do know that they somehow don't mix. Because when we look at quantum theory, there is no gravity in there. Gravity doesn't figure in there. And time itself is an external dimension. It's a classical parameter in quantum theory. Time, T, yeah, in the equations. So there are certain limitations when it comes to quantum theory. Time is still a mystery. We don't know what time is. Time doesn't emerge out of quantum theory. And gravitation doesn't even exist in quantum theory. You try to bring gravitation into it, it breaks down. Gravity doesn't work in the ultra microscopic world. There is no need for gravity in quantum mechanics somehow. And you try to quantize gravity, it doesn't work. And there are very clear ways in which it doesn't work. You try to create, let's say you try to construct a black hole through quantum mechanics. You can do it. You can construct a mathematical black hole in the ultra microscopic domain. You can take a pure mass, a point particle of pure mass, and use the rules of quantum mechanics to create a black hole. It will be different from the black holes that the general theory of relativity gives us. Very different. The Schrödinger radius it doesn't figure in a quantum black hole. It's a different kind of radius that you get there, and so on. So there are differences, and these two theories somehow we are unable to reconcile them. So I don't have an answer as to what would be a joining bridge between them. We need to find somehow a way of quantizing gravity. We still don't have it. People have been trying for a long time. That's why string theory became a thing. We're trying to figure out a new way of doing this, and string theory has not solved any problems. So these are two very different theories. One is about the ultra microscopic world from which reality emerges. The other is about the large scale structure of reality. Both work extremely well, but there is a disconnect between the two. And the disconnect is apparent when we try to look at black holes in the quantum domain. That's why you get these singularities, these infinities, which is division by zero, which is unphysical. When you have a singularity, it's telling you that your equation has broken down. It is giving you an unphysical result. So we have singularities in general relativity, which tells you that the equations of general relativity break down at the ultra microscopic scale, which means we need better equations, which means we need to amend the theory somehow in such a way that it works at the quantum scale. As of today, we don't have answers. That is the situation as of today. The 21st century was supposed to be the century in which we figured out what gravity is. In the last 22 years, we have made not 1 inch of progress. That's where we are. And that's why physics is so interesting, because there is so much to discover. All right. Abhishek says, what is mass? What is the difference between mass and weight? What is mass and what is the difference between mass and weight? Mass essentially is the amount of matter in a body. Let's say you have a ball that contains 1 kilogram of mass. You take that ball, you put it on the surface of the earth, it will weigh 1 kilogram, yeah? You take it to the moon, it will weigh 1/6 of the weight that it has on earth. So the amount of matter inside that ball is the same. But if it is on the surface of the earth, it will weigh 1 kilogram. If it is on the surface of the moon, it will weigh 1/6 of a kilogram. You take it to Jupiter, it will have a different weight. You take it to Saturn, it will have a different weight. You take it to Pluto, it will have a different weight, and so on. So, weight is the effect of gravity on a mass, and mass is the amount of matter that is contained in a body. Another way of looking at mass is its equivalent energy by E equals mc squared. So you can convert mass into energy. Generally, we talk about electron volts, keV, mev, gev, etc., kilo electron volts, mega electron volts, and so on, which is the equivalent energy of of a certain mass. So a mass remains the same, but its weight changes depending on where it is. So that is roughly the difference between mass and weight. Okay, Pranav says, as you said earlier, mathematics is the language of physics. And I'm trying to self-study physics. So it would be great if you could recommend what are the different types of mathematics necessary to understand physics in brief. And are there any book recommendations by you? The mathematics that you need for physics, you essentially need to know a lot of math. Math is like a toolkit which you need to solve problems in physics. So you would need to know infinite series, power series, complex numbers, linear algebra, calculus, differentiation, integration, partial differentiation, partial integrals, multiple integrals, ordinary differential equations, partial differential equations, vector analysis, tensor analysis, Fourier series, power series, calculus of variations, special functions, series solutions of differential equations, Legendre functions, Bessel functions, Hermite polynomials, Laguerre functions, partial differential equations, like I said, functions of a complex variable, probability, statistics, the whole lot. That's a whole lot of math that you need to know in order to actually do physics. Without math, you can't do physics. You need to master all of these different areas of math. Would I recommend any books? Well, if you know the basics, if you at the college level or something or university level, I would recommend Mathematical Methods of Physics by Mary Bose. And I have a bunch of books here. Mary Bose is a good place to start off with. Or you could take any of these topics and pick up the Shrom series book for these topics and work out all the problems, and you get good at that. And that's how you get good at physics. Once you go deep into mathematics, you will realize you're actually doing physics, because math is the language of physics. For instance, if you take the book on differential equations by Tenenbaum and Pollard, you go deeper into it, you'll realize that the problems you're solving are physics problems. That's how it is. So yes, math is the language of physics. You need to build your own massive toolkit. You need to understand lots of different kind of math, different branches of math, and only if you do that can you actually do physics at the level of the big boys or big girls. Math is the difference between the grown-ups and the kids. You can understand physics conceptually. You can speak about physics and talk physics and discuss physics and all that, but you can't do physics unless you're good at math. So you got to do it. Okay, Sachin says Stephenson 218 is the biggest star that has been discovered thus far. Is there a possibility that it has its own solar system? If yes, would its solar system have a lot of planets since its solar mass is so much? So this star is apparently the largest star that has ever been discovered. Millions of times more massive than the sun. Its diameter, its radius is so big that if that star where the sun is today, then its surface would exceed the orbit of Saturn. So, in case you know, the planets in our solar system are Mercury, Venus, Earth, Mars, Saturn, Jupiter, Uranus, Neptune, Pluto. So that star would engulf the orbit of Saturn. And if you want to look at what this star would look like compared to the sun, let me show you a nice image. Let me show you a comparison. Take a look at this. So Stephenson 218 is on the right, and the sun is a small little dot on the left over here. That is how enormous this star is. So that's what Stephenson 218 looks like. It's called a hypergiant star. It's, I mean, it's at the limit of how large a star can get. Now, the thing about these hypergiant stars is that they are so massive that they burn out their nuclear fuel very, very rapidly. The sun, our sun, has a lifetime of about 10 billion years. 10 billion. A hypergiant like Stephenson 218 would have a lifetime of about a few million years only. It's a very short-lived star, extremely short-lived star. If it is so short-lived, most likely there's not even enough time for planets to form around it. Or if planets do form around it, they would be very rudimentary, very, very hot protoplanets, and eventually the star will die, most likely in a hypernova or something. Maybe, I'm not quite sure what is the life cycle of this sort of star, what is the end stage. But yeah, if there is a solar system, most likely it's just debris, very hot debris. It is very unlikely for planets to form in such a short period of time. If planets do form, those would be very hot and very rudimentary balls of fire, or lava. That's what it would be like, and that's all it is. All right. Okay, my friends, we are at the end of the questions. Let me take some questions from the live chat. You have questions? Ask me now on the live chat. I will take a few questions before we end this session. So, Dunga Singh Chauhan, my views on the new monkeypox. I have no idea what it is. Um, every few months, a new virus comes into the picture. Yeah, I don't have any views. I don't think it's a serious issue. When do you think our civilization will reach the second scale in the Kardashev scale? Maybe in the next 100,000 years, if we survive that long. Maybe never. We don't know. It's just pure speculation. We don't quite know. Does the double slit experiment prove the existence of Maya that Vedanta talks about? What exactly collapses the wave function? A conscious observer. Um, we don't know. What collapses the wave function? There are different theories about what collapses the wave function. Is it consciousness that causes collapse? Is it something else that causes collapse? There are experiments in which there is no conscious observer. The observer is just a mechanical apparatus, and yet the wave function collapses. So we don't know. Maya, I mean, you cannot mix spirituality and religion and faith with science. You can't do it. I think I have to keep repeating this for the rest of my life. Yeah, you cannot mix science and spirituality. Don't mix science and religion. Don't mix science and philosophy. Don't mix. Science is about observables. And Maya and all this, how do you define Maya from the scientific perspective? So let's not mix Vedanta and science. I have the highest amount of respect for our culture, for Vedanta, but it doesn't mix with science. Science is different. We India is the birthplace of science. We know that, right? And our scientists did not mix faith with science. Otherwise, you can't do science. So please, my dear friends, please understand this. You can't mix these things. Okay, let's take some other questions. A few other questions. I can see some questions that have been answered already very recently. Um, uh, Okay, sir. Thank you so much. I am greatly enlightened. Thank you. Veda means science. All right. Thank you. No, there is no way to prove that souls exist. You can't. Can you measure a soul? Can you observe a soul? Can you do? Is there a clear scientific definition of a soul? Is the soul an observable entity, measurable entity? It's not, right? It's an unphysical entity, and therefore you cannot talk about souls in science, and therefore you can't prove it. You either believe in it or you don't, but you can't prove it. It is non-falsifiable. All right, let's take some questions from science. Okay, as the galaxies are so far away, what is there between galaxies? You have empty space between galaxies. It's mostly vacuum. And you have the cosmic microwave background radiation, the relic radiation, which is left over from the Big Bang. You could call it you could consider it to be the afterglow of the Big Bang, which is extremely cold radiation, 2.75 degrees Kelvin, just barely above 0 Kelvin, right? And you have what is almost vacuum, but that vacuum is not empty. It's teeming with virtual particle antiparticle pairs, which you will understand if you study uh, quantum field theory. So it's empty space, but that empty space is not quite empty. It's actually teeming with particle antiparticle pairs, virtual particle antiparticle pairs. That's what lies between galaxies. So from our perspective, it's just empty space. Empty space, very, 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 very thin, diffuse. You would see some protons, cosmic ray protons, antiprotons, etc., flying around. A few, sometimes atoms of hydrogen, perhaps, but very few and far between. It's an almost perfect vacuum. Okay, what next? Please answer, sir. What would you like me to answer, sir? What if the sun is suddenly replaced by a black hole? Well, we would not know for about 8 minutes. After 8 minutes, the light will disappear because it takes 8 minutes for the light to travel from the sun to the earth. So if the light stops being emitted from the sun, it will take 8 minutes for us to know. And after that, it will be darkness. But the earth will remain in orbit around this new object, the black hole. And provided the black hole has the same mass as the sun, then none of the orbits of the various planets and other bodies in the solar system would change. They would stay exactly the same and nothing else would happen. The only thing that will change is that the light source will disappear and everything will freeze. And that's what happens. Nothing else. Okay. Couple more questions. Does infinity exist in the real world? Infinity is actually unphysical. Let me give you a different perspective. Infinities do exist, and infinities of different sizes. Think about it like this. How many numbers do we have between 0 and 10? Construct a number line. Start with 0, 0, 1, 2, 3, 4, 5, all the way up to 10. We have 10 numbers between 0 and 10. It's from 0 to 10, right? But between 0 and 1, you have all the decimals, right? 0.1, 0.2, 0.3. Between 0 and 0.1, you have further decimals, 0.01, 0.02. So between any two numbers, there is an infinite number of numbers. Between 0 and 1, there is an infinite number of numbers. Between 0 and 10 also, there is an infinite number of numbers. And these two infinities have different sizes, don't they? Isn't that perplexing? Isn't that strange? But it's true. So infinities do exist, mathematically at least, and infinities are not all equal. Infinities can come in different sizes. Some infinities are larger, some infinities are smaller. So that's how it is. That is a strange thing about science and mathematics. Sir, let's discuss about James Webb Telescope in detail. What's its purpose? I think I have already discussed in detail. Its purpose is to give us a much more detailed understanding of the universe in the infrared domain. It will allow us to look deeper into the universe, look further back in time, because the Hubble telescope did not have the ability to observe the universe in infrared wavelengths. And because of the expansion of the universe, which is still continuing, the oldest light in the universe, which was about 230 or so million years after the Big Bang, the oldest light in the universe, which was emitted at that time, it has been stretched out beyond the visible wavelengths into the infrared wavelengths. So the Hubble Space Telescope simply cannot see that old light. The James Webb Space Telescope can see it. It is purpose built to observe the universe in the infrared spectrum, right? And that's why it's going to be able to look back further in time than the Hubble Space Telescope. So that is the purpose. It's going to give us a much sharper uh, image of various objects it observes. We are already seeing that, and it's going to be able to show us galaxies that are the possibly the first galaxies that ever formed. So we will get a whole different perspective on the universe, right? So I have discussed that in multiple episodes. You need to look at that. I have also spoken about the damage that suffered in this episode itself, and I have discussed the images in the previous episode, one of the previous episodes. Look it up, please. All right, sir. Okay. Is there anything else? What if the Himalayas did not exist? If they did not exist, they would not exist. Is the moon artificial? The rotation of the moon of the earth is real mysterious. The distance between the moon and its satellite is very large compared to other planets. Which satellite does the moon have? What's the evidence that the moon is artificial? Do you have any evidence that somebody made it? That maybe some government made it? Let's see something else. What if humans did not exist? Then we would not be having this discussion. All right, I think we are done. Ruchika says it got damaged. Yes, I have spoken about this at least twice in this episode. Yes, it got damaged. Very minor damage. It's going to be fine. Okay, my dear friends, we are done. We are at the end of today's episode. Thank you very much for your questions, and I will see you in the next episode. Until then, take care. Thank you again, and see you very soon. Bye.